Hello and welcome back to the discussion sessions of the Production Technology Theory and Practice course. So, let me remind you that in our last session we have discussed in details that how the performance of a grinding wheel can be defined by 5 parameters, particularly the abrasive types of the abrasive grain, then the size of the abrasive grain, next is the grade, then the structure and the bonding material. Particularly in this sequence, we have to define by a letter and a digit, followed by a letter and then digit and a letter, that how the grinding wheel can be selected, what kind of grinding wheel you have to select depending on the situation or the combination of the work material, okay, and the parameters are being used. Okay. Next, let us see what kind of grinding processes are there in practice. Okay. Now, if the axis of the grinding wheel is horizontal, then like in case of milling operation, it is called the horizontal grinding, and since the horizontal grinding is used for making a flat surface, so this is called the horizontal surface grinding. Okay. Now, in case of horizontal surface grinding, the rotational speed is given to the wheel, that is the wheel speed, and it will reciprocate to cover the entire width, all right. And of course, there will be a feed given, and that feed is called the in feed in case of grinding. So, the work speed given to the workpiece which will reciprocate. Okay. So, this is a combination of the relative movements, wheel speed wheel rotating like this and getting a cross feed, plus the in feed to get the depth of cut. In feed is given once, okay, you understand that, and when it will be ground, after that it will be again given the in feed if it is required. So, it is incremental, as you understand that. In case there is a round shape workpiece, in this case the same movement will be done by the wheel, that is the wheel will be rotating, it will be given a cross feed and an in feed, plus the workpiece will be rotating. Okay. So, here the workpiece is reciprocating because it is a rectangular workpiece, here it is a round shape. So, it will be rotating about this axis. So, these axis of the workpiece and the axis of the grinding wheel will be perpendicular to each other. Now, if the axis of the grinding wheel is vertical, it is called the vertical surface grinding, and the vertical surface grinding, in this case the wheel rotates about its center and then in feed is given, and in case of rectangular workpiece like in here, it will reciprocate, okay, along the direction of the in feed or perpendicular to the in feed and the axis of the grinding wheel. Okay. In feed given here along the axis of the grinding wheel and perpendicular to the work speed. Here it is the same, in feed is given, wheels is rotating about the axis of the grinding wheel, and in case of the rotating job, that is a round shape job, then the work has to be rotated like in case of this. Okay. So, only difference is that in both cases it will be the surface to be made, but here it is with the horizontal axis of the grinding wheel, here with the vertical axis of the grinding wheel, otherwise this is the similar. Okay. Now, for horizontal for vertical grinding, there is also a grinding wheel which is not shown here, which is of the cup type, okay, like this cup type, and the grinding wheel I am roughly making this. So, this is the grinding and this is the grains, and here it will be axis of rotation and this is the workpiece. Okay. So, this also surface, so that means the workpiece will be rotating and the grinding wheel also be rotating. So, this is the cup type, here of course, it is mounted, and this is the arbor. So, this is the cup type grinding wheel for making the flat surface as well. So, this also vertical, okay, vertical surface grinding, because it is a surface which is produced ultimately. Here it is shown in the two dimensional picture. This is the wheel rotation, the horizontal surface. Here is the cup type actually. So, this is the reciprocating when it is the rectangular job, and when it is a circular job it will actually rotate, it will be rotating. Okay. So, this is the also vertical surface grinding. This is the internal and this is the external cylindrical grinding. That means, here is the workpiece and the external cylindrical surface will be ground by this wheel. In this case, as you can see, the workpiece and the wheel both are rotating in the same direction, all right. And in this case also there is a wheel which is inside the workpiece, that means it will be for grinding the inside hole, okay, inner hole of the workpiece or a cylindrical workpiece. So, the workpiece will be rotating in this direction, in the clockwise direction, and in the anti-clockwise direction the wheel will be rotating. Okay. This is how it is shown. This is the axis of the grinding wheel, this is the axis of the workpiece. Okay. This is how it is, it can be represented in the pictorial view. The same thing is given in the pictorial view, that this is for the external cylindrical grindings given. That means, here the wheels will be rotating about this axis, and parallel, this axis is parallel to the workpiece axis if it is a cylindrical, of course. And since the outer cylindrical surface is being ground, so therefore, the grinding will be in touch with the outer cylindrical surface. In feed will be given to take the depth, and the in case of the internal hole, okay, this is the grinding wheel which is on the arbor, and grinding wheel will be rotating in the opposite direction of the workpiece, and the in feed will be given to take the depth. Okay. And here you will see that this is the freshly ground surface. All right. So, in this case what we get is that there is already a drilled hole. Okay. The drilled hole is rimmed and then it is ground. Okay. And while grinding we are actually increasing this hole diameter a little bit, but we are increasing the surface finish more. Okay. So, the emphasis is given for the internal grinding of a hole on the surface finish rather than removal of the material, because most of the material is removed by drilling, okay, followed by rimming if it is required a little bit, as I said, and the rimming also for increasing the surface finish of the internal hole. Of course, here for internal cylindrical grinding, the traverse feed motion is given to the mandrel along with the grinding wheel. So, it will be rotating as well as it will be traversing inside the hole of the cylindrical job. This is an external centerless grinding. This is an unique process where the workpiece is not held by anything, it is just loosely supported by the rest blade between the grinding wheel and a regulating wheel. This is called the regulating wheel. Okay. So, regulating wheel, by the way, can also be a grinding wheel. All right. Now, grinding wheel is rotating in this direction, in the opposite direction. Here in this direction, as you can see, opposite direction is the rotating is the workpiece, and in the same direction the regulating wheel is rotating. Okay. So, as a result, what happens that the regulating wheel will determine the surface speed of the workpiece, all right, and the grinding wheel will grind, of course, the surface. So, the regulating wheel, the role of the regulating wheel is to support the workpiece, to define the surface speed, peripheral speed of the workpiece and to feed the workpiece. So, in this case the external centerless grinding, a very thin and long rods can be ground. Let us say for example, the needles, very thin needles. Okay. So, you cannot grind those needles part by part, small part by part, okay, because needles are small in length, each needle. So, normally what is done is a big part, very high length is ground and then it is cut off into small pieces, all right. So, that very big, but the very small diameter will be very fragile, in the sense that this will not be very stable, okay, and it will be flexible. If you cannot hold that on the at the ends, you cannot hold it in a chuck. So, therefore, they have to be simply supported, and between the two wheels, one is the grinding wheel, one is the supporting wheel, it actually goes in as it is shown here, and the regulating wheel, okay, this is located with respect to the grinding wheel at an angle of roughly it is about 3 to 5 degree, okay, very small angle, 3 to 5 degree angle. The purpose of this is that when the very thin rod, which is the workpiece to be ground, this is passed through the grinding wheel and the regulating wheel, this has to be given a feed as well. It has to go forward, so that the entire length, which can be very big, the entire length is ground. Okay. So, to give the feed, there is nothing to give the feed, meaning that there is no additional device, additional movement given to the workpiece. So, it has to be given by the rotation of the grinding wheel and the regulating wheel. So, therefore, the regulating wheel is located at an angle of 3 to 5 degree with respect to the axis of the wheel. So, this is the axis of the wheel and this is the axis of the wheel and this is the axis of the regulating wheel. So, this is about 3 to 5 degree, that is what I said here. Now, since it is inclined, okay, so at this, along this there will be a force W r and the d by 2. Let us say d r is the regulating wheel. So, W r is the I will draw it in a better way, so that it actually looks better. So, I will extend this is the axis, okay, and this angle is 3 to 5 degree, as I said. So, now along this axis, when it is rotating, there will be a force. This force can be defined by W r d r by 2. So, W r is the angular frequency of rotation, angular rotational frequency of the regulating wheel, okay, and d r is the diameter of the regulating wheel. So, it is the radius d r by 2. So, therefore, this force will have a component at this direction along the axis of the workpiece, which will be what, W r d r by 2 and the sine of, let us say this is theta, okay, which is 3 to 5 degree, sine of the theta. So, this is the feed force, we will call it, and the feed force is the one which is actually dragging or moving the workpiece in this way, all right. So, the workpiece will be then ground along the entire length and of course, the diameter, because the rotational frequency to the workpiece is defined by the surface of the regulating wheel. Okay. So, this is the mechanism how the external centerless grinding works, and this is used for, as I said, the pins, okay, needles, particularly the pins of the thrust bearing. Thrust bearings are used in practice in very large number, and the bearing elements are very small rollers or the pins, very thin. So, those are made with the help of the ground, with the help of the external centerless cylindrical grinding, centerless grinding, and there, as I said once again, that work is not supported, workpiece is not supported by anything, it is just held by a knife, Okay. This is the rest blade, it is called, on which it is resting. Okay. This is the grinding machine. A small grinding machine like this we can see in the lab also, I will tell you there. Now, in this we have the bed, okay, like all the lathe machines, milling machines and so on. We have the column, here we have the wheel head located. This is the apron that I was talking about. This is also called the wheel guard, because the wheel rotates at a very high speed. I said this is 10 to 80 meter per second. So, at this speed the wheel, if it breaks, then each part broken part can actually fly with a very high speed, and that could be very dangerous. So, always before switching on this grinding wheel or the grinding machine, the apron or the wheel guard should be there. Now, this is how the in feed is given. Okay. This is the feed which is the cross feed. This is along the axis of the milling cutter, in case it is horizontal milling cutter, and this is the work speed that I have already shown it to you in other slides, and this is the grinding wheel. So, this is the entire grinding machine. Okay. Now, let us see that, like in case of the turning, in turning you remember we have discussed the mechanics of turning process or mechanics of metal removal in turning overall. So, there we have discussed the models like Merchant's model, like Lee and Schaefer model, to look into the mechanics of the metal cutting, and that mechanics told us that how to correlate the forces with the angles. Now, the abrasive machining process, this is a little different than the turning in the sense of the tool, because the tool which is grinding wheel in case of grinding process is absolutely different than the single point cutting tool, because in the grinding process, in the grinding wheel, each grain can be considered as single point cutting tool. Okay. But the difference is that in case of single point cutting tool, each tool has a certain geometry. It has the rake angle, okay, particular rake angle. Either it can be a 0 degree rake angle, or it can be negative, but it can be positive rake angle. Okay. But in case of the grinding wheel, the rake angles are random, okay, or angles are random. We cannot define a small grain of a certain value of the rake angle, you should understand that. Okay. So, therefore, the angles are random and the grains are randomly oriented also. How you orient a grain particularly in a position, it cannot be defined, because you are adding them in random, and then you are adding the bonding material, then you are churning it, and you are making the grinding wheel. So, therefore, it is large in number, grains are large in number, and each grain can be considered as a single point cutting tool. Okay. Grains geometry is random, this is randomly located and randomly oriented within the grinding wheel. This is how the grinding wheel or the grinding process differs from the turning process, for example. And in case of mechanics, when we are defining the mechanics of the process, therefore, they have to be, it has to be defined with respect to the grinding wheel, okay, in case of grinding. Let us see how it is, what it is. In the grinding process, we draw this schematically using one grain. Let us say this is one grain located in the grinding wheel, and the grinding wheel center is here. Okay, this is the center of the grinding wheel. So, therefore, and this is of course the workpiece. In the workpiece, one grain is removing the chip. So, this is the chip, small chip which is removed by one grain. Okay. So, subsequently you will understand the next grain will come and remove such a piece of chip, and so on. All right. From this center of the grinding wheel, this is the radius of the grinding wheel, you understand that. Okay. From here, therefore, this is also radius. Now, I already told you earlier also that you do not get confused, because this is a position, okay, from here to here. this is the grinding wheel. If I extend it, this will be the grinding wheel. Okay, this is the grinding wheel and this is the center. So, as this Vf is given, this Vf is the feed velocity of the workpiece. So, this is the workpiece. So, as a combination of the rotation of the grinding wheel and the Vf, so the grinding wheel rotates in this direction and the Vf is given. So, therefore, this point moves from here to here. This is the other location of the or other this thing of the grinding wheel, all right. It can go like that. So, it can go like this if you extend it and so on. So, therefore, the grinding wheel diameter is shifting, sorry, the center is shifting like this and one grain is making a chip like this. So, this chip is shown here, that this is the chip which is made by one grain. I will remove that, otherwise it will disturb in understanding. Okay. Now, in this the geometrically we can actually establish the relationship between the angle, okay, let us say this is a small angle, and the parameters like the diameter of the grinding wheel. This is the T1 maximum, this is the uncut thickness, okay, and from here to here this is the length of a chip that is being formed. Okay. Now, this is the depth of cut, D is the depth of cut, I think it is given, yeah, here it is given depth of cut, okay. L is the average length of the chip, here it is given. Capital D is the grinding wheel diameter. So, this is the radius, this is also the radius, all right. B is the width of cut. Now, the width of cut you can find out from here, like if this is the workpiece. So, this will be the width of cut and this okay, B, it is given as the B. So, this B is given in here, this is the by the chip you can also determine, all right. Now, from this chip that is being removed by one tooth, you understand that this will be in the 3 dimensional, it will be like this, all right. So, it will be the maximum width, this is the maximum width, because this will be how the chip is, this is how the chip is formed, and since this is the length, chip length, okay, chip length, this from distance from here to here will be the T1 maximum. This is the uncut thickness. This is T1 maximum is the maximum uncut thickness. Okay. Or here actually we will not call it the maximum uncut thickness, but let us say the chip thickness we will call it. This is the maximum thickness, all right, because otherwise it will be confusing with the T1 in case of the turning. In case of turning, we said that the T1 is the uncut thickness, T2 is the chip thickness. So, here it is the chip thickness actually, okay, because this is already made chip, already produced chip. Now, there is a concept of grinding ratio. Grinding ratio is given by the ratio of the B max here and the half of the T1 max, this one. Okay. This is approximately given as the 10 to 20 in practice. Now, let me explain it to you why it is half of T1 maximum. I already told you that since the T1 varies from, in case of milling, T1 varies from 0 to maximum, the T1 average is taken and T1 average is roughly half of the T1 maximum. Okay. This is how we take it in case of milling also, because there also it is the same chip, same kind of a chip that is produced, and therefore, the grinding ratio is given by the maximum width of the chip divided by half of the T1 maximum. Okay. This is in practice, as I said, roughly about 10 to 20 depending on the type of the workpiece material that we have. Okay. Now, the volume of a chip, if the chip is like this, we consider this to be triangular. the volume of a chip is given by half of B1 maximum, okay, T1 maximum into the length of the chip, all right. So, then if we put here the value of the gamma g, which is 2 B max by T1 max, okay, here, then it will be 1 by 4 T1 max already here. So, T1 another T1 max will give you T1 maximum square into gamma g into L. So, we have put it here the value of the gamma g, and we are getting this equation as the volume of a chip. Okay. So, here we have to find out the value of the L, all right, this length. To get that, we say that the average chip length can be found out if we consider this to be a very small angle as d by 2 approximately, d by 2 into beta. This is like this, d by 2 into this angle, this will be roughly the value of the L. Okay. Now, the L can be then expressed in terms of beta as the d by 2 into, if this value can be of this nature, that is 2 root over d by d. Why it is that? Because the cos beta from this triangle, okay, the cos beta is equal to this divided by this. Okay. So, this is d by 2 minus d. Okay, you can see from this here I have repeated the drawing, so that I did not have to go to the other page. From this triangle, okay, we are taking that cos of the beta. Cos of beta is d by 2, sorry, here d by 2 minus depth, that is this value, okay, divided by capital D by 2. So, this will be 1 minus 2 depth divided by diameter from here. Now, sin beta, this is root over 1 minus cos square beta, and if you do that, this will be 1 minus 2 d by d, and if we ignore that, let us say this is 0, very small. So, this is approximately 4 d by root over 4 d by capital D, 4 depth of cut divided by capital D. This will be equal to 2 root over depth of cut divided by diameter of the milling cutter. Okay. So, therefore, the beta, if the beta angle is small, so sin beta is beta. So, this is approximately equal to 2 root over d by d. Okay. Now, you get this value beta, and you put this 2 root over d by d, small d by capital D, which will be equal to root over capital D into small d. Now, the volume of the chip, we have already found out that this is equal to 1 by 4 T1 maximum square gamma g into L. So, in this place we can find out that the value of the L, since it is this. So, we can put the value of the root over diameter and the depth of cut, and we get this value. Okay. So, this is the volume of a chip. Now, the volume of material removal per second, which is also the material removal rate, okay, this is given by the velocity into area. Okay. This is velocity into area that we have shown earlier, like in case of the any other processes, that material removal rate overall will be given as a product of velocity and area. So, here the velocity is Vf, okay. This is the velocity that we have to take, because this is responsible for the material removal, it is given the feed here, okay. And the area will be the depth of cut and the width. Width we already said, right. So, this is the width, this is the width and the d. There it was written b, but here also it is b. So, it is the b into this d. B into d is the area and Vf is the velocity. So, to make it second, we are dividing by 60. So, this is the material removal rate. Okay. So, we found out the volume of a chip, material removal rate, and then we can find out the number of chips produced per second. See, the number of chips produced per second, this will depend on basic three things. One is the wheel speed, second is the width, okay, and the third parameter is the grain concentration, that how much grain is located in unit volume of the or unit wheel area. Okay. So, here we are writing the same thing, that the number of chip produced per second, okay, will be the wheel speed pi d n, d is the diameter of the wheel, n is the rotational frequency of the wheel, b is the width, all right, c is the grain concentration. Grain concentration means the number of active grains, that is per wheel unit area, per unit wheel area, okay, and divided by 60, because we have to, this is RPM, revolution per minute. So, this is multiplied by 60 is second. So, these three parameters can be correlated, that is the volume of material removal, volume of a chip and the number of chips produced. How? It is very simple, that the volume of chip, volume of one chip into the number of chips produced, this is in fact is the material removal rate. Okay. Once again, volume of one chip into the number of chips produced, this is the total volume. So, this is the volume of material removal. So, then if you write the equation that 1 by 4 gamma g T1 maximum square root over capital D and the small d multiplied by the number of chips produced pi d n B c by 60, this is equal to MRR, which is B VF D divided by 60. This is what exactly we are writing here, this is the equation. Okay. Now, from this equation we can find out what is the value of the T1 maximum. If we simplify that, you will see that this will give you the T1 maximum value equal to root over, because this is square, root over 4 VF root over D divided by pi d n C gamma g. Gamma g is the grinding ratio, okay, root over small d is the, this should be small d, this should be capital D, I am sorry, you can correct it, this should be capital D, okay. D is the diameter of the grinding wheel. Now, here you can see that this is the capital D. So, this is a typo error. Now, the average force per grit, we will come to this from the FC. What is FC? We are coming here, we will explain here. Before that, let me explain it to you that why we have determined the T1 maximum, because the specific energy, like in other processes, if you have seen, if you remember, that specific energy we are defining through the specific energy constant and the uncut thickness. Okay. So, in case of turning, in this case it will be T1 average, like in case of the milling, we will say that the specific energy is equal to the specific energy constant into T1 average, and T1 average we have seen that this is half of the T1 maximum. Okay. So, half of T1 maximum is T1 average. So, therefore, this is the UC given by this factor. Then the power is given by FC into VC, and the VC will be the cutting velocity pi d n divided by 60 into 1000. 60 is to make it in second, and this is to make it in, this is in 1000. So, this is to convert the meter to millimeter. Okay. So, ultimately what we will get is that the power is FC into pi d n by 60 into 1000, and this is also given by, power is given by, I will write it, that this is FC and the VC. Also it is given by UC and the material removal rate. Yes. So, UC and the material removal rate is, we have found out, B VF D into 60, this is the area and the velocity, this is the material removal rate. So, UC into material removal rate is the power, which is also equal to FC into VC. So, this is the VC, cutting velocity, right, and this was also okay, just to change the unit. from this equation we can find out the value of the Fc is equal to this. Fc is what? Fc is the total tangential force, like if it is the grinding wheel for example, all right, and this is the workpiece, let us say. If this is rotating like this, workpiece moving like this, so this is the Fc, which is the total tangential force, okay, total tangential force, all right. Now, this total tangential force will be equal to, from this equation is this 1000 bVF duc divided by pi dn. Okay. Now, we can say that the average force per grit, because what happens is that this is the total tangential force and we are interested in the force which is acting on each of these grains, that is more important for us. I will tell you why. Okay. Now, therefore, the average force per grit will be this force which is distributed to all the grains which are located within that, right, within that sector where the force is acting. So, here this is the Fc, which is the total tangential force distributed to all these grains, which is within the width, within the length and the grain concentration. Okay. So, within that length, how many grains are there, that depends on the width and the grain concentration as well, okay, along with the length. So, therefore, Fc divided by BLC will be the average force per grit. So, this will define how much force each grain is experiencing. Okay. That can be found out from here. So, you get this, okay, get the UC is equal to U0 and the half of the T1 max to the power minus 0.4, put the value of the T1 maximum here and you will get this equation. So, we are avoiding all these constants, okay, 60, 1000, pi, 4 and so on, and we are saying that this is proportional to these factors. Okay. That U0, because you understand that Vf to the power minus 1, okay, Vf to the power minus 1, here we have to have the, somewhere here we will be having that. Okay. So, you will see that actually we will be finding out that Fc prime, this will be proportional to this, all right. Now, from here you can say that this Fc prime can be increased, okay, if we are increasing these factors, right, because it is directly proportional. That means, by increasing the Vf, by increasing the depth and by increasing the, or by decreasing the n and the d value. See, why we are not touching the C, because C is the property of the grinding wheel, this is the grain concentration. We have made, we already have the grinding wheel and the grinding wheel is already made. So, the grain concentration is already defined. Similarly, we are not touching here the U0 and the gamma g, because U0 is a constant, this is specific energy constant, okay, and that depends on the power that is given to the process, because this is specific energy consumed when the T1 is equal to 1 millimeter U0, that is the U0. So, therefore, we say that Fc prime can be increased if we are increasing the Vf and if we are increasing the small d, which is the depth of cut, all right, or by decreasing the n and the d, because C is constant again. Now, this is important conclusion, because we have to actually have a control over the Fc prime, because if Fc prime is increasing, that means the grain can be dislodged easily. Okay. Suppose there is a worn out grain and it is stuck there, it is not coming out because the bond is very strong. But then if that is for a particular force, if you are increasing the force on each of these grits, okay, then it may actually facilitate the grain dislodging. So, therefore, if we can increase that force per grit, the worn out grain can be dislodged easily, okay, or we can facilitate the dislodge process of the worn out grains. In that case, that problem of the hard wheel and the hard workpiece material when we are having the glazing, that problem may not be coming so frequently. In that case, what we are doing is we are making the grinding wheel look softer, okay, because we are manipulating these factors, that is the Vf, small d, n and the capital D. Okay. So, this is an important phenomena, an important conclusion, that how we can have a control over the grinding process by controlling these parameters, so that the grinding wheel would look softer. Actually, it is a hard grinding wheel, but we are manipulating with these factors, and then the grinding wheel is facilitated, that means the grains are facilitated to be dislodged. Okay. All right, now let us discuss some of the factors on which the specific energy depends. So, specific energy can be calculated through a total tangential force on the wheel. Okay. We already said that U c into MRR is the power. So, F c V c is the power, which is U c into MRR. So, therefore, U c can be given as V c F c, this is actually V c, we are calling this as a cutting force, okay. And the V f is the feed velocity, this is the feed, this is the cutting velocity, into the B and the D, which is area. So, area into velocity, this is the MRR, all right, material removal rate. This is how it is obtained. This I already shown it to you here also, okay. I think here we have shown it. So, the power is given by U c into MRR, and this is therefore equal to U c is equal to this. Now, the specific energy in grinding has been found to be an order of magnitude higher than that of a single point cutting, okay, such as turning. So, this specific energy in turning, with respect to turning in grinding process, this is very high, and this is explained by the fact that it has been shown experimentally that it increases rapidly when the chip thickness T1 average is decreased. Let us say the curve will be something like this, and this curve says that as the T1 average is small, for small T1 average the U c is very high. Okay. So, therefore, this reason actually helped us, this curve helped us to understand that why this specific energy in grinding is high. At very small chip thickness involved in the grinding, the plastic deformation occurs over an area having very few or no imperfection, and the material tends to behave like an ideal material with no inhomogeneities. Okay. Meaning that I already told you when we were discussing the defects, that when the defects or the imperfections, they move along with the lattice structure, then the force required to deform the material will be less. I told you that during the discussion on the imperfections. Okay. It happens the same way in case of grinding, that at a very small T1 uncut thickness or the depth, the imperfections are very less. Normally, the imperfections lie at little lower level than the top level of the top surface. Okay. So, therefore, when the grinding happens at the very small T1, then it is almost without any imperfection, and that layer acts like an ideal material. And when we have an ideal material, I have already shown it to you that for that the stress required is very high, maybe 1000 times higher. That means, this will be G by 2 pi if you remember. So, that was for the ideal material. This is what happens in practice for the in case of grinding, that in grinding it happens on a very low depth of cut, and at that layer, thin layer, the material behaves like an ideal material without any imperfection, and when there is without any layer without any imperfection, the force required to deform the material will be very high. Okay. So, therefore, the specific energy required will be very high in grinding. But this effect, that when the T1 is small and the UC is very high, because of that, this effect is called the size effect. Okay. Now, the increase in UC with decreasing chip thickness, this curve, this effect is called the size effect. Now, this, however, in case of grinding, the size effect is not the only effect because of which the accuracy, or sorry, the specific energy is very high. Here you can see it is stated that while size effect is an important factor contributing to high specific energy in grinding, evidence of excessive rubbing and plowing during the grinding have also been presented. So, in case of grinding, what happens, unlike in case of turning, when immediately the material removal starts taking place, in case of grinding, when it plunges to the workpiece, when it comes in contact with the workpiece, initially each grain it will first rub, okay, then it will plow the material, then only the material removal takes place. So, during that rubbing initially and then plowing, when the material is not segregated yet, I will show it to you in the curve, then the consumption of the power is very high and the specific energy becomes very high. Okay. So, that those two factors, that means the rubbing and the plowing along with the size effect, because it happens within the very small T1, the specific energy overall in grinding becomes very high. So, if you see this curve during the controlled plunge force plunge grinding here, or during the cutting experiments with single abrasive grain, this is the result. It has been found that under the light loads, when the load is still light, here in this x axis we have the normal force on wheel, okay, and along the y axis we have the radial depth of cut. Okay. So, now when the load is further increased, okay, first of all let us see that at very low light load there is almost no material removal, not almost, there is no material removal shown here, okay, because radial depth of cut is 0 still, and all the energy is consumed in that rubbing. So, initially if we consider one grain here, suppose this is the data that we are taking for material removal or the grinding process by one grain. So, the one grain, as I said, that initially it will start rubbing, then it will plow and then it will start removing the material. Okay. So, here for this low load, when the normal force on the wheel is low, at this the radial depth of cut is still 0, no material is removed. At this the plowing action starts and the material removal is not there really, because it is a plowing, here it is very low. Okay. So, the energy is consumed in this rubbing and the plowing, all right. When the load is further increased, plowing occurs where the material is simply pushed to the sides of the grooves, okay, generated by the abrasive grains on the wheel. It is still not removing the material, but the material is pushed to the sides, you know, like we plow the ground, we plow the rice field, you remember that. So, when it will plowed, see the material, that means the earth, okay, or the mud will be on the sides. Okay. Material removal or cutting occurs when the load is increased. So, at this value of the load, when the load has increased sufficiently, the material removal starts taking place. You can see that the radial depth of cut is significant. Okay. So, these three regions are shown here below. Thus, both size effects as well as rubbing and plowing, okay, significant factors contributing to the high specific energy in grinding. But this is a very specific characteristic of grinding, that in case of grinding the specific energy becomes very high. okay, in comparison to the comparable depth of cut or comparable T1 of the other processes like turning, for example. Because in case of turning, if you compare it with the grinding, the depth of cut is sufficiently large, so that the defects can be located there, dislocations can be there. Okay. And the same thing happens that I discussed it earlier. Instead of G by 2 pi, the stress that is required for removing the material along with the defects will be 1000 times less. So, in case of turning, for example, with the comparable T1, the specific energy reduces drastically in comparison to grinding. In grinding, it happens almost in the ideal depth or through the ideal material. Okay. All right. Now, if you see here that if you plot specific energy against the chip thickness in the log scale, let us say in the x axis we have the log of the time, okay. Log of the thickness, all right. And in this, so do not get confused, this we called as a T1 earlier also. So, it is here it is called the T, this is the one, okay. This is the T, here it is T average. In all these cases we have designated this as a T1. So, please do not get confused that this is also T1, this is a chip thickness. So, if we plot that in the log scale, the equation will be U c T1 to the power m, this will be constant, okay, or U c and the T to the power m is constant, which means that U c is inversely proportional to the T to the power m. Okay. In the fine grinding range, the value of exponent m, this m, is about 0.9, almost equal to 1. Okay. In the rough grinding range, the value of exponent is 0.6, okay. And for single point turning range, cutting range, the value of exponent is 0.2 only. So, can you see the difference here that in case of grinding, this exponent is almost 1. So, U c is proportional to 1 by T 1 in case of grinding, but this m value is about 0.2. So, this is significantly low, okay, meaning in the sense that in case of turning, this will not be like in case of grinding, it will not be the size effect, okay, but there will be defects, there will be dislocations, and the shear stress which is required to create the deformation, plastic deformation, will be much less in case of turning. Okay. Let us see the wheel wear. The wheel wears out in the following way, that we have the initial wear, initial break in, okay, steady wear, and the catastrophic wear. So, this curve is almost the same as we have shown it for the turning tool, all right. If we plot the volume of wheel wear against the volume of work material removal, so this will be the initial break in. Initially the sharp grains are there, so they will have high stress concentration. As soon as they come in contact with the workpiece, they will be dulled or they will be worn out quickly. So, this is the initial break in. After that, it will be very steady wear, because the wheel wear, the grains will be wearing out, but this worn out grains will also be dislodged, and then new grains will come. So, the overall wheel wear will be very gradual, it is a steady wear, that is why it is called the steady wear. After some time, the flats will be very high, that means grinding will the surface will have a very high worn out grains, and the wearing action takes place very rapidly, and the grinding wheel may fail actually, that is called the catastrophic wear. Okay. So, here it is written phase 1, this is rapid wear due to wearing of high spots on the wheel surface. Okay. Phase 2 is the rate of wheel is constant, as I said that it will be a gradual wear. Phase 3, here wheel becomes dull due to loading and developed a glazed appearance. Okay. So, loading and glazing I have already explained it to you, that once again if the wheel grains are worn out and they cannot be dislodged because the bonding or bonding material is very hard, in that case it is the wheel glazing. Okay. And if the grinding wheel structure is very closed, that means the voids are very small and the small chips get loaded there, get stuck there, cannot come out, then that surface will be glazed surface. Okay. So, phase 3 also it is the material removal rate is reduced because of these two factors, okay, and grinding forces are increased. So, therefore, because of that high grinding force and material removal rate, material removal is less, the wear can be more and more, and then at a certain point the wheel actually can break. Okay. Now, during stock removal, this is the rough grinding such as vertical surface grinding, abrasive cutoff, etc. Phase 2 almost extends infinitely, it goes very long. Okay. So, this is called the self sharpening action, is a continuous self sharpening action. I already explained it to you that the wheels will be the grains on the surface will be worn out, they will be dislodged, and then behind them there will be the sharp grains, and again those sharp grains will have the wearing action, it will go through the wearing and it will be dislodged, and then again sharp grains and so on. So, it will be a continuous self sharpening process, and therefore, this curve goes very long and it is a steady wear. There is practically no wheel dulling almost, which obviates the need for the dressing. So, in here the wheel dressing is not required because it will continuously be self sharpening and always there will be sharp grains on the wheel surface, okay, wheel face surface. So, there will be always more material removal, less force and the less power consumption, okay, because always the dull grains will be dislodged and the sharp grains will be coming out from behind the dull grains. Okay. Now, this is the way the grinding wheel actually wears. Okay. Now, these are the grains, those grains are rigidly connected to each other in the grinding wheel with the means of this bond. Okay. This is the binding material, this is the bond, all right, and the whole thing is the grinding wheel. Inside this is exaggerated heavily, and it is shown that how the grains are located in the grinding wheel. Now, this is the workpiece, okay, and the workpiece is given the Vf, which is the feed velocity, and the grinding wheel rotates in this direction. All right. Now, when the grinding wheel rotates, since it is in touch with the workpiece, these are the places where the grain will be in touch with the workpiece, and gradually this surface will be worn out of the grain. Okay. Then the wearing may happen within this line, or the wearing action, tool wear action or the grain wear action can happen within the bond also. So, how exactly these grain wearing action happens, the wear out of the grains happen, that I will explain in more details in our next session of discussion. Thank you for your attention.